Okay, so we're going to start. Actually, this is the last thing we'll have to do with chemical reactions and equations. After this, we'll talk about atoms, structures of atoms, and structures of molecules. All right, so this is called energy. All right, so let's take a look at this chemical reaction. This is combustion of methane. Say take methane in the presence of oxygen, you produce carbon dioxide and water. Alright, so methane is also known as natural gas, and what we use natural gas for when we burn it, and this is the burning of natural gas, is to produce heat. Okay, and really, this reaction here and a lot of chemical reactions we cover, especially the combustion reactions, you're not so much worried about your product. I mean, carbon dioxide and water. It's it's this guy right here, which we've left off up to this point. So what we're going to do now is start talking about the energy component of chemical reactions, which actually is probably one of the big deals about chemistry. Uh, the chemical reactions are great, okay, but the energy that's given off or taken in during a chemical reaction is sometimes and most times what is actually what we're looking for. So we're going to talk about heat and what it is, and etc. All right. So this is called thermochemistry, which is the study of energies given off or absorbed by chemical reactions. And they just don't have to be chemical reactions; they can be physical reactions like ice uh, melting, a change in states. Thermochemistry is a subset of thermodynamics, which is a study of heat transfer, heat flow. Just to let you know, heat is a form of energy transfer. Heat is really not a thing. It's the movement of energy, and it's a kind of energy, and that kind of energy is heat. And so, what is energy? Well, to do anything. So when you do something, you need to have energy. So energy is what is needed to do work, or what happens when heat is transferred. All right, in terms of energy, there's two broad types of energy. There's potential energy, which is stored where you can't see it. You can't see that it does energy, but you know it will do energy after you sort of let it go. And then there's kinetic energy, and kinetic energy is what really does move things. Kinetic energy, and really a lot of this energy ideas is all about physics. And I hope you take physics, because physics will cover this more in depth. We really do a really kind of elementary study of energy. I mean, really, what you do is you take physics, and if you really want to know how physics applies to chemistry, you take physical chemistry. But what we got to do is at least give you some idea what's going on. So, kinetic energy is energy due to motion. All right, and the formula for that is kinetic energy is equal to 1/2 the mass times velocity squared. Okay, anything that moves has energy, and what it can do is it can get other things to move by transferring its own energy to others. So the idea about energy is we're going to talk about in a minute. It's energy that cannot be created or destroyed, but what it can do is be transferred. So what you can do is you can take kinetic energy and turn it into potential energy, and back into kinetic energy. So let's say I pick up, there's a book lying on a table. What I can do is I can pick the book up, and that's kinetic energy. I'm lifting it up, and when I lift it up, hold it up in the air, and it's just sitting up there, it now has potential energy in it. And it's just sitting there, and the book has got energy in it. And once I let go of the book will move, kinetic energy, and it will maybe slam against something on the table and make a giant boom, okay, which is kinetic energy. So kinetic energy can be turned into potential energy, back into kinetic energy. Kinetic energy can be turned into kinetic energy. Potential energy cannot be turned directly into potential energy. It always has to go potential kinetic to potential. But kinetic energy can turn into kinetic energy. All right, potential energy is stored energy. Places where we see is like gravity, like holding a book up. The book has energy in it because when you let it go, it comes slamming down and gives off energy. Electricity, positive and negative charges. That's the battery. So a battery has a plus and minus, and the electrons want to move from the plus and minus, but they can't unless you let. And so what they do is that they really want to get to each other, and so there's energy between them, and then what you do is you put a wire between them, and then they move. Spring. You pull a spring, and the spring, you can feel it like it wants to unspring. Okay, so that's part of those. Chemical energy can be potential energy, and that can be stored in bonds. When you break a bond, it requires energy, and when you form bond, it will release energy, and we'll talk about those as we go down the road. Okay, so which of the following is an example of potential energy? Pencil rolls across the desk. Well, it's rolling, so it has kinetic energy. A pencil being sharpened has kinetic energy. Pencil is heated, that's kinetic energy. And pencil rests on a desk. Well, that means it's not really resting. What it means, it's there, but let's say it's on a slanted desk, okay, that may be held by your hand or something, and it's not moving. But once you move your hand, it rolls down a desk, so it would have potential energy. And the final one definitely has kinetic energy because it's falling. So it's D has potential energy. All right, increasing potential energy. And potential energy is a big deal in chemistry. We'll talk more about it when we talk about atomic structure. For instance, one way to increase potential energy. So if you let's say you take a book and you raise it a foot off the table and drop it. It'll go make a sound. Boom. Okay. Then you raise it up 10 feet and you drop it and it hits the table. It goes BAM. Okay. Well, when it got lifted higher up, it had higher potential energy than it did lower. And you can tell just by the sound that it's given off, because sound is kinetic energy. So when you move things away from what they're attracted to, they gain potential energy. Okay, if you put two magnets in the south and north pole close together, you let them go, they'll go boom. But if you pull them apart, they'll come zapping real close, real hard together. All right, so that's how you can increase potential energy, is by increasing the distance between them. You also can do the opposite. You can increase potential energy by pushing things together. And like in this slide, it says if you take a spring and compress it, you can feel that you're increasing the energy. If you take two magnets, two north poles, and push them together, as you get closer and closer and closer, it gets harder and harder to push them together. Okay, so again, you can increase the potential energy for things that repel each other by moving them closer together. So things that are attracted, you pull them apart, increases their potential energy. Things that are repelled, as you push them close together, you increase their potential energy. Okay, And so this is the opposite. All right. So a book that's closer to the table has less potential energy. Two magnets that are close together have less potential energy, and so forth. All right. Which of the following represents a decreased potential energy of a system? Book is raised 6 feet above the floor. Well, you're increasing it because it's going higher up. Ball rolling downhill. Yes, it's decreasing its energy because it's getting closer and closer, and so its potential energy is going down and down and down as it gets closer to the floor. Two electrons coming close together. Yes. No. Well, they're going to be increasing their potential energy because they repel each other. So if you take two things that repel each other and push them together, they increase the potential energy. Spring is stretched completely. You're increasing its potential energy. You know, it takes a lot of energy to pull that guy apart. And two atomic nuclei approach each other. Again, those are both positive charges. And just like C, they're going to repel each other, right? Which increases their potential energy. So B is the answer here. Okay. All right. So we talked about the law of conservation of matter, where matter cannot be created or destroyed, just transferred. Well, there's a equivalent statement for energy, where energy cannot be created or destroyed. What can only be transferred from one type to another. And what we're saying is that the total energy of the universe is always constant. That what it does is it just moves from one type of energy to another. So it might move from potential energy, kinetic energy. It might move from chemical energy to mechanical energy. But what we're saying is that if you were to count all the pieces of energy moving, they would still be there, but they just would change how they are moving. All right, they might start out as energy due to a book falling into molecules after they hit the table, causing the molecules on the table to move, which increases the heat in the table, which is energy. Okay, temperature and heat. Well, temperature has many interpretations. One way we can kind of think about it is temperature is a way to kind of measure the hotness of things. So something that's hot has a lot of heat in it. Now, heat has, so let's talk about heat in a minute, but right now, you know, we'll talk about an intuitive way of thinking about heat. But so temperature, something that has high temperature has a lot of heat in it. So if I had a baseball with not much heat in it, and another baseball with a lot of heat in it, the one baseball with a lot of heat in it would have temperature. Now, it's not technically right, but it's the kind of way we gotta think about it. If you get more into the physical chemistry and in the physics behind it, we get more in depth into it. Another way to think about temperature is molecules and atoms and particles. So the more the particles are moved, the more energy they have, and that energy increases the temperature. So what we say is that temperature is related to the speed of particles. So if you speed up particles, temperature will increase. Okay, heat. So heat really isn't a thing, it's more of a transfer. It's a transfer of a type of energy between temperature differences. And it always goes from warm to cold. And what it means is that cold is not really a term. It goes from a warm object to a less warm object. And what the heat does is it moves until both sides have the same temperature. So a molecular view of heat transfers. Hot, cold objects placed in contact. So cold means less hot, okay? Less heat, less molecular motion. So the molecules in a hot object are moving faster, okay? Then what happens is and when you put them close together, the hot molecules or particles will transfer their energy to the slow mover guys, colder, slow, less heat, and these guys will start warming up because they start moving faster because these guys bang into them. When these guys bang into them, they start to lose some of their energy, so their energy goes down, these energy goes up, and eventually everybody's energy is the same speed. Everybody has the same speed, and they all come to the same temperature, and this is called thermal equilibrium. Okay, let's talk about the units of energy. So we defined energy, at least kinetic energy, is equal to one half mass times velocity squared. So let's say I have a 2 kilogram object moving at 1 meter per second. So let's just plug in an equation. So you get 1/2 times 2, 1 meter per second, and then squared, and then go through blah blah the equation, and you get the units of energy are kilogram meters squared per second squared. And what we do is we wrap all those guys up into one term and call it a joule. So we won't deal with this. So we'll just have a unit of energy called a joule. Ideally, what you would like to always do is come back and see what it really means. But at this point, what we're going to do is just use this number, this unit, and work with it. If you have greater than 1,000 joules, we often use just turn it into kilojoules. So if you have 35,000 joules, that would be 35 kilojoules. So what you do is you just divide your joules by 1,000 and you'll get kilojoules. Right, another unit of energy typically is called a calorie. And everybody's probably heard of a calorie, and we'll talk about the calories you guys probably heard right over here. But the definition of a calorie is how much energy is required to raise 1 gram of water by 1 degree Celsius. Okay, so the relationship between a calorie and a joule is 4.184 joules per calorie, and etc. Now, when you talk about most people here, when they hear calories, like, oh, I burned 2,000 calories today. What that means is nutritional calories, which is a capital C. All right, so which is actually 1,000 calories. So if you say if you burn 1,000 calories a day, what you're really doing is burning 2 million, 1,000 times 1,000 calories. Okay, so actually 1 calorie, all right, is equal to 1,000 calories. And we won't be using the big C's. We'll be using little c calories. All right, which is the unit of energy? And hopefully we all pick joules here. Okay, pascals measure pressure, newtons measure force, watts measure power, amperes measure current, and you don't have to know that, but that's what they are. Okay, so heat. Let's say you pour hot coffee into a cold cup. And really what it means, cold cup means less warm cup. So there really is no such thing as cold. Cold is less warm. So you have really warm, less warm. Well, the heat's going to flow from the hot coffee to the less warm cup. With the fast water, the hot ones move faster, they bump and they transfer the kinetic energy. And eventually, all the cup and the coffee come to the same temperature. And as we said, that's called thermal equilibrium. Okay. So now let's start thinking about how this is going to relate to chemistry. So let's say you have a balloon and it's on a string and it's just sitting there. And when you look at it, it looks like it's doing nothing. It's just sitting there. But if you take a pin to it, it will release a pop, kaboom. And that kaboom is kinetic energy. It's sound. Sound is moving particles through the air, pushing air around. Okay, so where did that energy come from when you popped the balloon? Well, it had to come from inside the balloon. Okay, it just can't. It couldn't come nowhere. So when you popped the balloon released energy. So in a sense, the balloon looked like it had potential energy, just like if you have a book, you raise a book and you hold it up in the air and then you drop it and it hits the ground and it goes kaboom. You think of it as going from releasing its potential energy, its untapped energy. But if you look inside the balloon, what you'll notice is that there's particles flying around inside the balloon, but we can't see them. We can't see them because they're all inside the balloon. And you may go, well, if they're moving inside the balloon, then why aren't they affecting the balloon and having the balloon move around? Well, it's because there's 100 particles smashing into the wall over here on the left, and then there's 1,000 particles over here smashing on the right, and they balance each other out. So it looks like the balloon is going nowhere, but actually there's all this stuff going inside, but we can't see it. But it has internal energy. So it has all this stuff going inside, but we just can't get it because that energy is trapped inside the balloon, and it will stay in there until we untrap it. And when you untrap it, it goes flying out. So we're going to see that the balloon, in a sense, is what we call isolated system. And we'll talk about systems in a minute, but it's keeping all the energy and the particles inside it, and so everything is staying internal. So we're gonna talk about chemicals. Chemicals have internal energy as well. They have stored, packed up energy that we can't see until there's a chemical reaction takes place. All right, so when you look at the look inside the system, what you'll see is there's particles moving around, and they have kinetic energy. But there's also things that do definitely have potential energy, like a balloon. The balloon has potential energy because it's stretched, okay? But the particles inside have kinetic energy. So the total energy, internal energy of a balloon is its potential energy and its kinetic energy. But we just can't see it. Now, if you go back and look, so what we're going to be interested in is that suppose you have a balloon, a big balloon, and then you let air out and it gets smaller, okay? It's lost energy. And so what we'd like to do is be able to know what is the difference between a small balloon and a big balloon in terms of, well, you could do it in terms of their size, But the size of the balloon is determined by how much energy it has in it. Okay, a big balloon will have more internal energy than a little one because there's more particles flying around it than a little one. So, and we really can't measure the individual balloon energies. I can't measure the big balloon's energy and the little balloon's energy. But what I can do is actually measure the difference in their energies, which is going to be the change between the two energies. Okay, and so we'll see how that works in a few minutes. All right, so what we're going to do is talk about this thing called a system. Okay, and a system, basically what you can do is you can list information about a system. You can write down who's in it, like molecules and stuff, what its pressure is, what its temperature is, what its volume, the number of particles, a whole list of things. Just whatever you can measure of it as it sits right still. Okay. So a state function, and that's what we're talking about here, are state functions: pressure, temperature, volume, internal energy, okay, number of particles. It's what we can measure right now. It's independent of how we got there, all right, where we're going to go to. It is what it is right now. So if I have a balloon, I can measure how much pressure it has, how much temperature, its temperature, and its volume, and how many particles it have, and its internal energy. I don't care how it got there. The state function just tells me what is there right now. So if I have a temperature equal to 25 degrees Celsius, tells us all we need to know, and that's that the temperature is 25 degrees. Doesn't tell me how I got there, okay? It just means it's 25. Okay, now you can change the state of a system, all right? And it might, in this case, you increase the temperature to 35. It doesn't matter how you do it. You can take 5 different, you can add 1 degree at a time. You could add 10 degrees and then subtract 5 and add 10 and add 5. But all that matters is that the final distance, for instance, a state functions like this. So the change of state, change of temperature is a state function as well. Okay, so let's say I want to drive from Piqua to Dayton. Okay, all right. Well, I could take I-75 straight down, and it's 35 miles. I could also go east 40 miles and then go south 30 miles and then go back west 40 miles. All right. When you add the east and west together, they cancel each other out, and it's still 30 miles. So the change, it doesn't matter how you get there, okay? The change of temperature is how far it is from the final versus the initial. That's it. Straight line. You can kind of think of it. Okay, so the system has states. We want to define a system. All right, so here's an example. Here's our system. What we're interested to study, what's taking place inside a reaction taking inside a beaker. Well, that beaker's inside the room, all right, and the beaker's the system surrounding this room, and the barriers are the walls of the beaker and whatever's separating the beaker from the room. Okay, there are three types of system. There's open systems, which allow mass and energy to cross boundary. So that'd be like having a beaker or open beaker. Gas particles could come out and energy could leave as well. So energy and mass could leave the beaker. A closed system is where the only thing that can transfer is energy. So let's like you have a flask here with a cap on it. It releases gas, but the gas stays inside it. But the heat will move from the inside the flask to the outside the flask. So energy can move, but mass can't. That's called a closed system. So exchange from system to surroundings. An isolated system is where nothing can move between systems and surroundings. And this is like the internal energy. So internal energy is where all the it's like a thermos, all right, or whatever. Is all you can't feel it getting. You got a hot thing, and you can't. Your hand doesn't get hot or cold, but you know it's hot inside it. Okay, so there's neither exchange of energy or mass between surroundings and system. We will be dealing mostly with closed systems. Okay. So a closed system include the surroundings, absorb energy, mass, no change. Okay. So it's this guy here. So a closed system can absorb, lose energy, but not mass. Okay, heat. Well, as we talked about at the very beginning, what we're interested in a lot of chemical reactions is how much heat is given off and so forth. Well, it turns out that we cannot, so we symbolize heat as Q, is that we can't measure heat directly. But we know that heat can be gained or lost by an object. And one of the things we know is that if temperature, if an object changes its temperature, for instance, if you add heat, the temperature increases. So one way to measure the amount of heat, to measure heat is to measure temperature. So if temperature goes up, you know you added heat. If temperature goes down, then that means you remove heat. So you know that there's a definite relationship between the change in temperature and amount of heat. This little tilde, remember, is a relationship. And it's directly proportional, as that means if you increase one, the other one increases, and so forth. Okay, so that's the first relationship. Is that heat is related to change in temperature. So let's stick with change in temperature. Suppose you heat a gallon of water and a cup of water, and you have them on the same heater at the same, you turn them both up to 10, and then you want to know which one's going to heat up faster. You're right over there. Yep, you're right. It's a cup. The cup heats up faster. Why is that? Because there's less particles. Okay, so smaller masses have bigger changes in temperature than larger masses. So if you increase the mass, it will decrease the change in temperature. So if we look at the change in temperature, if you increase the mass, okay, it means temperature will go down. Okay, so the way that write that mathematically is that the change in temperature is inversely proportional. So we say 1 over the mass. So we have two relationships. We have temperature directly proportional, and change temperature directly proportional to heat, and a change in temperature is directly proportional or inversely proportional to mass. Now suppose you have 1 pound of water and 1 pound of aluminum, put them in an oven and with the same amount of heat. Which one would change its temperature better? Well, if you don't know, and I've done it before, the aluminum will get hotter faster. And why is that? Because it can change its temperature better. So what we do, so there's a property of substances to gain or change their temperature determined based on heat. Some can change their temperature better than others. And some can't. And so what we do is we actually have this. We have a property called which measures the substance's quality of inability or inertia to change the temperature. And this is called the specific heat capacity, or C. So in this case, given the same amount of heat and mass of a substance like water, it is harder to change the temperature of water. So water has a higher specific heat capacity. That means it's harder to change the temperature. So heat capacity is like the temperature inertia. It's like mass. Things that are really massive are hard to move. Okay, things with high heat capacities are hard to move their temperature. Okay, so substances with high C's, heat capacities, will have smaller changes in temperature. And this is a really big deal in terms of our world, our life as human beings. And I wish we were in class. I would spend more time on it. But what we come down to is the change in temperature is inversely proportional to the heat capacity. So something that has a high heat capacity doesn't change its temperature very much. So it's inversely proportional. So when we tie it together, those three different relationships, we get this equation. The change in temperature is equal, not tilde, the heat divided by the mass and the heat capacity. But the main thing about this equation right here is now we have a way to measure heat. Well, all we have to do is rearrange the equation for Q, and we get Q equals mc delta T. Okay, so we can't measure Q directly, but we can measure change in temperature. We can, if we know C in mass, we can put all these guys together and figure this out, and that's what we're going to do in a bit. And here's different heat capacities of different substances. So if you look at gold heats up really fast. It doesn't. If you take you put it out in the sun, it'll warm up really fast. Versus if you take the same amount as if you put the water out in the sun, it won't heat up as fast. Okay, so lower guys heat up faster and higher guys heat up slower. Okay, so let's do all right, calculate the specific heat of a metal if it takes 235 joules to raise the temperature 32.91 grams sampled by 2.53 Celsius. All right, so what we're going to do is solve for C. Rearrange the equation, and you get Q divided by m delta T, and you plug it in, and you get that the heat capacity of this metal is 2.82 joules per gram per Celsius. If you went back at on the previous slide, you can see that actually this is a pretty high heat capacity, which means it doesn't change temperature all that well. Okay, the specific heat of copper metal is 0.385 joules per gram Celsius. How many joules heat are necessary to raise the temperature of 1.42 kilograms from 25 to 88.5 Celsius. So we're going to use that equation, and so what we're going to do is solve for Q. So Q equals MC delta T. And also what we're going to have to do is we're going to have to change 1.42 to grams so that matches my heat capacity. So this could be 1,420 grams. All right, so Q equals M C delta T. All right, there you go. And multiply them together and you get your number. Okay, so heat flow. Heat flow moves from more warm to less warm. Okay, okay, so the heat that moves from one object, the other object's gonna accept the amount of heat, same amount of heat. So if A loses 20 amounts of heat, B is going to gain 20 amount of heat. So what we get is that the amount of heat that Q1 loses is the amount of Q2 that gains. So a piece of warm iron is placed into a beaker of cool water. The iron loses 10 joules of heat. The water gains 10 joules of heat. Okay, so that's what happened there. So the iron lost 10 joules of heat to water, picked up the 10 joules. Right, a cast iron skillet is moved from a hot oven to a sink of water, which is false. The water heats. Okay, so you have a hot, so hot moves to cold, so the water's going to warm up, skillet's going to cool down. The heat transfer from the skillet has a negative sign. That's true because it's losing heat. The heat transfer from the skillet is the same as the heat transfer from the water. And that is also true. So they all look true to me. The water heats up, yes. The skillet cools, yes. The heat transfer from the skillet has a negative sign, yes, because it's losing heat. The heat transfer from the skillet is the same as the heat transfer to the water. Okay, this should be to the water. All right, so what we have here is, let's take a look at an example. All right, so using heat capacity. So let's say I have a 5 gram ball bearing and it's at 260 degrees Celsius. And I drop it into a cup of water that weighs 250 grams. When I drop it in the water, the temperature of the water goes from 25 degrees to 37.3 degrees Celsius. And what I want to do is figure out the heat capacity of the ball bearing in joules per Kelvin, grams Kelvin. And what I need, this should be grams Kelvin. So, so you have the heat capacity of water. Right. So what I know is that the heat of the ball bearing is going to, the minus should be over here. So the minus the loss of the ball bearing should equal the gain in the water. So it doesn't matter which side you put the minus, but technically it should be over on this side. But so the minus QB equals QW, but I'll put the minus here and we're okay. Now the thing is, remember that Q, any Q is equal to MC delta T. So the Q, the heat of the ball bearing, is equal to its mass times its heat capacity times change in temperature equals minus the mass of water, heat capacity, and the change in temperature water. And so the question asks is, what is the heat capacity of the ball bearing? So what I do is I just rearrange equation for the heat capacity of the ball bearing, and you get this. And what you do You plug the numbers. First of all, you find out the change of temperature. Change of temperature water. So it's change of temperature water is final. Subtract initial. So the final temperature is 30 to 7.3 degrees. Initial temperature was 25. So it increased by 12.3. There should be a plus there. What's the change in the ball bearing? Well, final temperature was 37, and it started at 260. So the temperature of the ball bearing went from 260 to 37.3. So it decreased by 222.7 degrees. Okay, now what we do is plug everything in. So we're going back to our equation. So the heat capacity of the ball bearing is equal to this equation. So it's going to be 250 grams, the mass of the ball bearing of the water, the heat capacity of water. Okay, remember minus something of -1 is the same as saying joules per over grams. So this could be joules over grams Celsius, or it could be -1s. Times plus 12.3 Celsius times 5 grams, the mass of the ball bearing, times the change in temperature. Now if you notice, what's going to happen to the signs is negative times a negative is positive. Alright, and the grams cancel out, and Celsius cancel out there, and you're left with the units, 11.6 joules per gram per Celsius. Okay, here's another one. Let's say if a 38.6 gram piece of gold absorbs 297 joules of heat, what will the final temperature of the gold be if the initial temperature is 24.5 degrees? Okay, the specific heat of the gold is 0.129 joules grams Celsius. Right, and so what I want to do is to figure out the final temperature. I'll have to figure out the change in temperature and then add that to the initial temperature. Okay, so I'm going to use my Q equals MC delta T, rearrange the equation so I get delta T equals Q over MC. So I just plug everything in. So Q is 297 joules. The mass of the gold is 38.6. Heat capacity is 0.129 joules Kelvin. Celsius. And then when you do the math, the joules cancel out, grams cancel out, and it was Celsius. And so the change in temperature is 59.6 degrees Celsius. Then you add that to your initial temperature, which is 24.5, and then so new temperature is 84.1. Alright, so now what we're going to do is apply this to actual chemical reactions. So what happens in chemistry? Well, you're going to make bonds, break bonds, and that's a whole lot of stuff on there. But really we're going to just pay attention to the energy that's given off or absorbed in a chemical reaction. And I'm going to skip over this one as well. Alright, so the idea that, let's think about it like this. Alright, we'll get to chemistry in a minute. But consider a balloon again. On the left is the initial state of a balloon, and on the right is the final state of the balloon. And the initial balloon has lots of internal energy than the final balloon. And the size of the balloon, like I said before, is related to its internal energy. Alright, so a balloon that is bigger has more particles in it bouncing around, and so has more internal energy, while a little y has less. Well, what I want to know is what is the internal energy difference between the two? Well, you can't go inside there and measure all these particles, and you can't go inside here and measure all their particles' energy. But one thing you can do is that you can have this guy change into this guy, and then measure this. Okay, so let's say you have your balloon here, and then what you do is you let air out. And you know when you let air out of a balloon, you hear a sound. Okay, and that pith sound is energy. All right, and that energy, that amount of energy is the amount of energy difference between this guy and this guy. Okay, it's not so. And the way that gave off the energy is this sound. Okay, so if somehow you could measure this energy over here, what you could do is measure the energy difference between this guy, internal energy, this guy, and that guy. So what happened is the internal energy of this guy, it lost some of that internal energy, and it turned into this energy, which I could measure. Okay. So the difference between these two internal energy is this amount of this sound. All right. So if you could measure this sound here, it's exactly the difference between the inner energy of this guy, internal energy of this guy. So what we can do is kind of write it like this: is that the initial balloon had a higher internal energy, so this is like a graph, than the final balloon by this amount of energy here. Okay, so if you can measure this energy here, what you could do, and that's the amount of energy here, and it goes down. So just like in a graph, when things go down, it's negative. If it went up, it's positive. So this guy loses energy, and so the energy would go down, released. Okay, so now let's apply this to chemistry. So let's say I have a reaction where products, so there are two kinds of reaction dealing with heat. There's exothermic and endothermic. Exothermic reactions are ones that give off heat. You can definitely feel them. The surroundings get warmer. Okay, then this is the case of like methane, gasoline, burning wood. Okay, your surroundings gets warmer. Why is that? It's because the system is giving off heat. All right, the reactant loses energy when it turns into a product, and the energy is given off as heat. So the difference between the two energies, this guy's energy and this energy, is the amount of heat that's given off. So let's look at that reaction. So here's your initial. So methane and oxygen before you do the chemical reaction. And then after you do the chemical reaction, so it's got a lot of internal energy. After you do the chemical reaction, it has less internal energy. And instead of giving off a sound, heat is given off. And we can measure the heat, the tree law released. And that amount, we can measure that using our formulas that we just talked about. And that heat, that energy here, is the difference between the internal energies of this guy and this guy. So in this case, exothermic reactions will always look like this, where the internal energy of the reactant will have a higher energy than the internal energy of the product. Always goes down, and heat is given off. Energy, it doesn't have to be heat, it's usually is heat. But so the difference between these two guys' energies is the amount of energy that's released. And it goes down, so it's negative. All right, then you have endothermic reactions, and they're the opposite. It's where you take where you add energy to the reactant makes the product. Here we have one to do with photosynthesis. One I'd like to think about is ice. So when ice turns into water, what you do is the ice absorbs heat from your hand. So what happens is ice plus heat produces water. So that's an endothermic reaction because heat is being absorbed into the ice to make water. So if we look at this reaction here, photosynthesis, you have carbon dioxide plus water plus energy. It could be heat, but in this case it's solar energy. Is added to these two guys, and what they do is they produce something that has more internal energy, glucose and oxygen. Okay, so it's being absorbed. Endo means in. So in this type of reaction, actually you're going to feel it's going to feel colder. So if you put your hand around this reaction, it'd feel like it was actually things could be cooling down like ice. When you put ice in your hand and when it melts, your hand gets colder because what's happening is the heat from your hand is moving into the ice, and that heat plus the ice is melting and making water. So on the term of endothermic reaction, the surroundings gets colder. And this is the reverse. Okay, so here's your reactant, and your reactant, and you have to add heat to it to make your product. Okay, for exothermic reaction, these are upside down, where the reactant was up here and the product was down here. All right, so usually chemical reactions we talk about, we have a constant pressure, and when there's constant pressure, the internal energy we talk about is given the name enthalpy H. What we want to know in our chemistry, what is the difference between the enthalpy of the reactant and the enthalpy of the product? I forgot to put product here. And the way to do that is because you can't measure the enthalpies directly, but what you can do is you can measure the heat that's released or gained in a reaction. And that heat is the difference between the two enthalpies. And that's where we're going to go from here. And how do we measure heat? Well, we can't measure directly, but what we can do is that we can use our formula here to figure out heat. And if we know heat, we can figure out the enthalpy change. Okay, so let's consider an exothermic reaction in a closed system. So a closed system means that energy can move between the surroundings and the system, but no mass. And say, okay, the reaction takes place, the reactant loses enthalpy. So the reactant becomes product and it loses some of the enthalpy. That's this guy here, energy. Okay, now that energy will leave the system, and when it leaves the system, it turns into heat. And then what you can do is you can measure the amount of change in temperature. And we know if you can measure the change in temperature and you know the mass and the heat capacity, you can figure out Q. Okay. So what we have is the heat losing system equals the gain in the Q of the surroundings. So this energy here is going to heat up the surroundings. Alright, so the Q of the surroundings is equal to the mass of the surroundings times the heat capacity of the surroundings plus times the change in temperature of the surroundings. So what we have is that through all this relationship is that the delta H, the change in enthalpy between the reactant and product, is equal to the loss in the enthalpy is equal to the increase of the surroundings, which is equal to the mass, the heat capacity, and temperature. So what I'll do is I'll measure the change in temperature, and if I have the heat capacity and mass, that will equal Q, which is equal to H. Okay, so indirectly I can figure out H by finding out Q, which indirectly I can find by this. And that's the key. And what we're going to do that. Okay, so what we're going to do empirically, experimentally, is use this thing called water calorimeter. Calorimeter means it's a way of meter calories, which measures heat. So calories are heat, measuring heat. And the key thing here is water's the surroundings. And what we need to know is the mass of the water. We need to know its initial temperature and its heat capacity. And we know, we can figure all those out. And then what we do is we do the reaction. And then what we do is we measure the change in temperature. The change in temperature is due to the system losing energy and heating up the water. So the system loses energy minus heats up the water, which we can find by using this formula here. So indirectly, the change in enthalpy between the reactant and the product is going to be measured by measuring the mass, the heat capacity, and change in water. Okay, so let's do a problem. Let's say I have 2 grams of methane and it's combusted in water calorimeter, and a temperature of the 250 gram water, so that's the mass of the water bath, increases from 22 to 26. And the heat capacity of water is 1 calorie per gram Celsius, or we could do in joules, but we're going to do in calories. And what we want to know is what is the difference in enthalpy, called the enthalpy of reaction, and is this exothermic or endothermic, and what has more enthalpy, the reactant or product. All right, so from a relationship is that the change in enthalpy is equal to the loss in loss of energy of the reactant to the product will heat up the water, which is related to this value here. So we need to find delta T. It's plus 404. And then we plug it in, and we get, for this reaction, there's 101 calories. Okay, and then we have this minus sign, and so we get the amount of heat that's lost from the reaction is minus 101 calories. Okay, the reaction is exothermic. Exo means out, so temperature, so heat is given out. Therm means heat, exo means out, so out goes heat, releases heat, and we'd expect it, the temperature to, the releases, gives off, loses, falls, energy goes down. So this is an exothermic reaction, and we get the reactant that has more enthalpy than a product. Okay, because the heat went down, so the product had less energy than the beginning by the amount of heat that's given off by this amount here. Okay, next step. That's nice, but what we want to do actually is find out the change in enthalpy per gram of methane, and really also the change in enthalpy per mole of methane. Well, we start out with 2 grams of methane, so we know there's the change in delta H is equal to 101 calories per 2 grams. So for 1 gram, it's going to be 50.5 calories per gram methane. Now to figure out in terms of moles, we need to figure out how many moles 2 grams is, which is 0.125. The molar mass of methane is 16. And then you just divide negative 101 calories by 0.125 moles, and you get this. All right. Okay, here's another calorimeter problem. Oops. You have 4 grams of ammonium nitrate is dissolved in a calorimeter. The temperature of the 250 gram water bath increases from 32, should say decrease, from 32 to 26. Okay, and here's our reaction here. And what we want to do is, what is the enthalpy difference between the starting product and ending product? Is it exo or endothermic? And which has more enthalpy, the reactor product? Well, let's just think about it conceptually. So it's getting colder. All right, so that means is that heat must be going into the reactant to make the product. So the product is going to have higher enthalpy than the reactant. So this is an endothermic reaction. Okay, so we'll see how that all works out. All right, so we got our equation. So indirectly, the change in enthalpy is related to the heat, the water change heat, which is equal to this, and we plug everything in. And we get the change in, so now we get negative here and a negative, so the temperature goes down. Negative times negative is positive. So the delta H is positive. So actually there's heat being added. Endo means in heat, absorbs heat, and you expect it to be positive. All right, and now we want to have it per gram. So it's going to be 1,500 calories per 4 grams of the substance. And you do the math. And then figure out enthalpy per mole. Find out the molar mass of the substance, 80 grams. Divide 4 by 80, you get 0.05 moles. And then, so you get 30,000. 1,500 calories per 0.05 moles substance, which is 30,000 calories per mole, which is positive 30 kilocalories per mole. Okay, now whenever we look at enthalpies, they can kind of be confusing, but so there are all kinds of different reactions measuring changes in enthalpies. If you're measuring the change of enthalpy in just a reaction, you don't care what kind of reaction it is. We call it the change. All you want to know is the difference between the reactant and product. It's called a delta H reactions, okay, or the change of enthalpy of the reaction. If you want to know the change in enthalpy between the starting materials, the final materials or molecule, that's called the delta H formation. If you want to know, like we just did it, if you dissolve the ammonium nitrate in water, that had a delta H, and that was called the delta H of solvation. When you melt ice or freeze ice, that has a delta H, okay, and it's called delta H fusion, and so forth. So the key thing is here is that there are all kinds of delta H's, and they're given specific names, but basically they all find the same thing. They find out the energy difference between the product and the reactant. Depending on the type of reaction, the subscript is given the particular number here, the name. The other thing is that change in enthalpy is also called the difference in enthalpy. Okay, so A going to B changes, so when A goes to B, there's a change in the enthalpy from A to B, but the change is the same as a difference, okay? The other thing is that enthalpies are also often just called heat of formation, reaction, or whatever, instead of calling enthalpy. So the enthalpy of reaction is often just called the heat of reaction. And the reason why that is because before they understood this, all they knew is that the reaction gave off heat. They didn't understand where it was coming from. So they actually thought when something when A went to B and released heat, that A was hotter than B, and it released the heat. But that's not the case. Um, A is not hotter than B. It just has more internal energy, and the energy is given off as heat. That used to confuse me all the time. When I saw heat of an enthalpy, I go, what is it? It's just the same thing. Okay, so now what we want to do, so what we did is we had a way empirically to figure out the enthalpy change by using a calorimeter. Now what we're going to do is there another way of doing it where I can just use data to help me to figure out the change in enthalpy? And that's what we're going to do now. There's going to be two ways. One where we're going to use standard heats of formation. The other one, we're going to use something called Hess's law. All right. First of all, is we're going to use this thing called standard heat of formation, and all these tabulated heats are all done at the same temperature and pressure, and we just want to. Then it's just to tell you what this is. So just want to be consistent with all our numbers. They're just not random numbers done at all different temperatures. Everything is, what you want to do is just have one thing to measure, and that's the enthalpy. And you don't want to have temperature, pressure, or anything else mess around with it. And here's the table. It's kind of blurry, but you can find this in books and so forth. So I just downloaded this from the internet somewhere. But here's standard heats of formation, or delta H's for the formation. So for instance, let's say I want to look at Al2O3. So what this means is how much energy, what is the difference of energy between the reactant and product? So how much energy did it take to make, or release to make Al2O3 out of aluminum and oxygen at 25 degrees, 1 atmosphere. Okay, and the amount of energy was released during this reaction was 1675.7 kilojoules per mole. And we're assuming that everything is constant. So all these guys are all kind of related to each other because they're all in the same situation. Okay. Okay, so I know this is a long PowerPoint, and hopefully I'll be able to load it up. So you're probably going to want to watch it in parts. And so what I want to do is find the delta H of a reaction, and I'll call it Rxn, using the standard heats of formation for this reaction here. So the first thing you need to do is write out the reaction, and then what you do is you make a table. And then what you go with, so you got this. So this N232 yields 2NH3. And then what you do is you go to the previous table of delta H's, and you find these particular values. So N2 0, H2 is 0, and NH3 is negative 18.6 kilojoules. All right, you put those in the table here, and then what you do is the formula is you're going to take the sum of the products. So you're going to add all the product side, and then you're going to add all the reactants, and then you're going to subtract them from each other. So the equation is the sum of the sum of the products heat of formations minus the sum, sigma means sum, of the reactants heat of formations will give you your delta H, and we're going to need to put the coefficient. All right, so pay attention to this. So I'm going to divide this into two parts. This is the product side. This is going to be the reactant side. So you have to add the coefficient. So it's going to be 2 times negative 18.6 kilojoules per mole. And when you do that, you can see the moles cancel out and left with kilojoules. Right, so that's, you're done with the product side. Right, so you're done with this guy. Now you have to do this. So there's a minus sign, minus. Now you'll add up all the product side. So the reactant side. So now you have 3 moles of hydrogen times 0, and 1 mole times 0 is 0. Okay, so this is the sum of all the product side, which is 0. And then you subtract this guy from this guy, and you just end up with 37.2 kilojoule per reaction. So every time you just do this reaction, one recipe will give off 37.2 kilojoules per mole. Okay, so this one turned out a little screwy in the transfer, but maybe I can fix it after, and I'll try to do that. But so then you won't know what I'm even talking about. But anyways, so I want to take a look at this reaction, the combustion of ethane. So here's the balanced equation. The 2 ethanes plus 7 oxygens yields 4 carbon dioxides and 6 waters. So what I do is I go to the table, find the individual guys. So ethane is negative 84.68 kilojoules per mole. I can leave that off. Oxygen is 0. CO2 gas is 393.5. And water liquid, make the status important, is negative 187.7. So I put everything in. And then what I do is I set up my formulas here. So here's my formula, the sum of the products minus sum of reactants. Okay, so I'm going to take, so there's 4 moles, which is 4 moles of carbon dioxide, times 393.5 kilojoules plus 6 moles of water times its enthalpy, and that completes the product side, minus, now let's do the reactant side, 2 moles of methane times negative 84.68 plus 7 moles of oxygen, 0. Okay, so this number here is equal to this. That 6 times is this. 2 times 84 is this, and then this. And then you just do the math. And so these 2 added are this. And negative times negative is positive. That's why we have a plus here. So that's that. And so what you have is that when this reaction takes place, for every one recipe, every time this takes place, there are 2,530.84 kilojoules of energy release. Okay, in the previous problem, the heat associated with the reaction is 2530.84 kilojoules per recipe. So I want to use this in a stoichiometry problem. So let's say I have 10 moles of ethane, and I want to know how much energy is released or absorbed. Well, what I do is I put the 10 here and I figure out how many recipes. I see there's 5 recipes. Well, every recipe you have 2530, so you take that 2530 5 times to be 12,654. Okay, now it's your turn. Give it a try. You can shut off the video and try your own, or you keep listening here. Okay, so I set it up. Same as before. Here's my chemical reaction, and here's my values from the table. And these are kilojoules per mole. And I have my sum of products minus sum of reactants. Okay, so I do the reactants first. So it's 1 mole times... Oh, I got a backwards here. All right, I'll fix that. So you get this and this, this and this, and there you go. All right. Okay. Now, one of the things that I want to make sure you know is that we talk chemical reactions can be reversible, and we haven't talked about that a lot. But if this particular reaction, the combustion of methane, gives off 802.3 kilojoules, the reverse reaction would require energy. So when you flip the equation, okay, the energy is the opposite. It becomes, if it was an exothermic reaction, it becomes an endothermic reaction. Okay, the other thing is that usually we just talk about A going to B. All right. But you could have a reaction start from R, turns into A, turns into B, and then into P. Okay? Well, when you look at the overall energy between this pathway and this pathway, it's going to be exactly the same. It's like my trip from Pickwood to Dayton. If I could take I-75, or I could go east 40 miles, go south 30 miles, and then west 30 miles, okay? The difference is going to be the same. So what we're going to be looking at now is that we can take many pathways to get to our end, but they should always give you the exact same value. Okay, so here's an example. So let's say I take carbon, add it to oxygen to form carbon dioxide. That's simple. That's a one-step reaction. But actually you can do it in 2 steps. You can take the carbon and make carbon monoxide. And then you could take the carbon monoxide and add oxygen and form carbon dioxide. And then what you do is you add the 2 equations together, and you'll see that the carbon monoxides cancel out, and you end up with our original equation. Okay, and so if you add up the energies of the first step and second step, you'll end up with this, which is exactly the same as this. So no, it doesn't matter how many steps you take to go from A to B, it's going to be the same as going directly from A to B. And that's where we go now. And that's going to be this Hess's law of heat of summations. And so what we're going to do is, it's got a lot of applications. But what we're going to do is just dive into it and do some problems. Okay, so let's say I have this reaction here where I have carbon, which is a solid graphite. So graphic like your pencil. And then what you do is you pass hydrogen over it. You can form C2H2, which is acetylene, which we use in our welding. Okay, so you can do it one step. You can just take the graphite and the hydrogen and make acetylene. Okay, another way to do it is you can take acetylene, and then oxygen to make carbon dioxide and water. And then you could take this guy and this guy. So you can use these three equations here to make this guy. So what I want to do is see how I can rearrange these three equations to come up with this equation here. And finally figure out what is the delta H. So the way that I usually do these is I look at each of the substances. So I'll take the C first, and I look for, so I start with C, solid graphite, and I look at what equation has that, and that's going to be B. And I can see that this has the C on the same side as this, so I don't, that's good. But the problem is that I only have, there's only one C here and there's two here. So what I have to do is I have to multiply this whole thing by 2 to get the same amount of graphite. So I take the whole equation and multiply everything by 2. So I multiply this 2 by this 2, this 2, and this by 2. Right, that's what I got. Right, next thing I look is the H2. What equation has H2? It's equation number C. And I see that the H is on the left side and this is on the left side, so that's good. So I don't have to do anything. I also notice is that there's a 1 in front and there's a 1 in front, so I don't have to do anything else. So this is good. I don't have to do anything else to this guy. Okay. Now I look at this guy, C2H2. So I find the equation that's in, it's in A, but it's on the wrong side. Okay, so what I have to do is I have to flip the equation like this. Okay, it's the right coefficient, so I don't have to do anything there. But what I have to do is I flip the equation, I have to change the sign. Okay, so I got 3 equations, and hopefully everything will work out. You know, don't make it complicated. What you do is you just take, and you'll see in the next couple problems how to do these more. So I'm going to take these 3 equations that I just, this guy here, this and this, and put them all together. So this is my first equation where I doubled everything. And this is my second equation where I didn't do anything. And this is the third equation where I flipped and change the sign. Okay, right, and what you do is you take all these guys, add them together, so it's this plus this plus this plus this plus this plus this, this, and this, all right, equals this plus this plus this plus this, all right, the product side. And then what you do is whatever is on the reactant side in the product side, you can cancel them out. So I have 2 O2s and 1.5 here, and I have 5 half O2s over here. So that's 2.5 O2s. Well, 5 halves is 2.5. So they cancel out. So I get rid of them. So now I'm left with this. Right, now if I look over here, I have an H2O and H2O. So now I can cancel them out, and I'm left with this. Okay, now I have carbon dioxide, 2 of them, cancel them out, and I'm left with this, which is my original equation. So they check out. So what I can do now is just add up the enthalpies, and there's my answer. Okay, so let's do another one. Okay, so pay attention how this works. So you're gonna, this is the, I want to figure out the delta H for this reaction here. So I'm given these reactions. So what I want to do is first look at the NH3. Right. So what equation has the NH3 as B? I can see that it's on the wrong side, so I'm gonna have to flip it and I'm also going to have to times it by 2 because I need 4. So I'm going to have to change the sign of this to plus and multiply it by 2. Alright, so I multiply this by 2, this by 2, and this by 2 and flip it. So it's this right here. Alright, now I'm going to look at the O2. And if you look, there's O2 in too many places, so I don't want to mess with that. And hopefully it'll work out. So if you have substance in many places, best just to leave it to, it probably will work out. Okay, next thing is look for the NO. Right, it's right here. So the only place there is NO is in A, and there's 2 of them. Well, it's on the right, it's on the correct side, it's on the product side, so you don't have to do anything, but you need to multiply it by 2. So what you're going to do is you're going to multiply this whole equation by 2, and you have to multiply energy by that. Okay, and finally, water. Okay, you need 6 waters. The water's found in C, and it's on the correct side of the equation. It's on the product side. But there's 6 of them, so you have to multiply everything by 3. So it'd be 6 H2s, 3 O2s, and 6 H2s, and 3 times this. Okay, we'll add it together and hopefully the oxygens will work out. Okay, so this is our goal to get this. Hopefully it'll all work out. So I have this equation, this equation, this equation. And so I add all 3 of these guys up. 4 NH3 plus 2 and 2 O2 and 6 H2s and 3 O2s. The net yields 2 of these, 6 of these, 4 of these, and 6 of these. Alright, so what I'm going to say is I noticed is that right off the bat there's 2 N2s on both sides. Cancel them out, and I'm left with this. I noticed that there's 6 H2s on both sides. Cancel them out. I'm left with this. Okay, there's 2 O2s and 3 O2s here. I can add them up. Give me 5 O2s. And so I have 4 NH3s plus 5 O2s yields 4 NO and 6 H2. And that's exactly what I hoped for. So since it worked out, what you do is you add everything together. So you get take then the enthalpies and add them all together, and you get that. Okay, so that's it for this lecture. It's a long one, but it's a good one. All right, that's all.